Good afternoon, everyone. I hope you had a good break. Doesn't look like anyone has thought much about 152 because Piazza was eerily quiet. Anyway, so a couple of housekeeping things that I want to raise. First off, you should all have had your exam score in your Git repo. There were a small number of students where I am unsure whether I graded what they actually submitted. If you find that the scores that you got have no relationship with what you think you submitted, please see me either after class or preferably in my office. Yes?
The letter next to that's the actual grade, right?
Yes.
Oh, okay, just want to make sure.
Yes.
So the total score is at 50?
It's 45. And so if you have questions about the grading scale or something like that, just put it on Piazza. But I want to make sure that everyone checks that I have the final thing. If for whatever is not, don't touch any of the files in your repo. We'll just straighten it out from there. When looking at the schedule, you may notice that I've taken out 2 homework assignments. We originally had 12 homework assignments scheduled, and I figured I'd rather have you spend the time at the end of the semester on the project, and I realize many of you have other projects as well, and I think we've certainly done a good amount of homework in this class, and we don't need to overdo it. So I did assign a homework assignment that I took from a source of what's called Nifty Assignments. So this is a Stanford professor who each year on this Computer Science Education Conference has like 5 or 6 other professors who came up with various nifty assignments. And so I listened to their presentation when I went to the conference. I said, oh, this is all very cool. And so this guy came up with this assignment to do these kinds of modern paintings. And so he pitched it as something that's good for recursion, functional programming, and all of that. And he did it in Haskell. And so you can actually read the source code of the solution in Haskell for what it's worth. Then I tried to just redo the same thing with Scheme, because I figured, hey, we just had this little lab where we did rectangles and circles in different colors, and here we have just rectangles in different colors. And then it took me a few minutes to figure out how do you do the borders around the rectangles, and I've given you the code for that. That's the magic line here. That gives you a colored rectangle with a black border. And then out of that, by just putting them into these HC and VC whatevers, one should be able to recreate what his project did. Then I try to follow exactly what he did. So the idea is that you start out with a large rectangle, and then you kind of cut it at a random spot in 2 smaller rectangles. And then you recursively do the same thing for the smaller ones. And sometimes you cut it horizontally, and sometimes you cut it vertically, and eventually you say these are getting too small, and then you color them in. And so I tried to actually follow his algorithm exactly, figuring that would be kind of cool if I got the exact same result as he did. And at some point I just gave up. His description wasn't so clear, and then I figured it was also going beyond what I wanted to do with this assignment. So his goal was to say, this is a non-trivial recursion. And so many students in his class, all the recursions they ever knew was factorial, and so he wanted to have something meatier than that. And so I think that's, of course, a noble goal. But you guys have been doing factorial and other recursions for a long time now, and so just practicing recursion that I wasn't all that interested in. What I was interested in is that you get the basic Scheme syntax under your belt, and it turns out to be a beautiful assignment for that, because you need to set up a bunch of functions, so you use define for that, or not. You need to have some kind of nesting, because you need to recursively at the same point define the function that does the helper thing and the function that does the whole thing. And so for that you have to use a letrec. You may remember there was a lab where you had to use let and let star and letrec. And so this one here drives home the point when you need to do what. And then you need to define various functions with lambdas, and then there's a little bit of list processing, because the random numbers, we're again going to be using the functional subset of the language here, and you can't generate random numbers in a functional language, because the way to do random numbers is by mutation. You keep changing something, the seed, and then you get the next random number out of that. So you're just going to be getting past a list of random numbers. And you just keep pulling them off that list, and that's your supply of random numbers. That turned out to be great for testing, because then I could give a very specific list of random numbers for testing and then the behavior was reproducible, and I could also figure out why the thing didn't work at first, because my solution didn't work at first either. And then eventually I figured it out. So that means that you have to do a little bit of list processing with first and second and tail and all that stuff. So it turned out my solution uses this list of constructs here. Define for defining a function, let star, and letrec, lambda, then some list processing, first, second does what you think it does, rest, list makes a list, maps a function to a list, cond and else does conditional processing. I needed modulo at some point, I can't remember where, for the random number generation, and plus, minus, star, slash, equal, and greater. Those are the constructs that I needed, so you shouldn't need to hunt around for anything more than that. So you know all of these constructs. And so at first I said, this is going to be a trivial exercise, because the recursion is well defined, the math is relatively straightforward. At some point you have to do some fractions and multiply something. Like if you have a width here and you know when to split it, at some place you need to multiply the width with the random number, and then you might need to add something to get to this point. But it wasn't like anything complicated. And then I watched myself typing up the solution. And so I've learned that whenever I type something and my fingers go on autopilot, which they routinely do, and they do for you too, right, when you type something that you know how to type, that maybe for me the solution is easier than for you, because it's unlikely that your fingers are going to be on autopilot. I have written 100 or 1,000 defines in my life, and lets and letrecs. You haven't. And so that then made me think about another presentation that I gave at a conference, where this is something that Professor Austin and myself did. So he's teaching 152. And so a year and a half ago, he was teaching 152 that was very heavily scheme or racket-based. And then he had some fun projects with some Bitcoin thing or something, I don't remember. And he was really dismayed. He said, how come that his students, they've been doing this racket stuff for a long time now, and the syntax is trivial, right? Parentheses, opening and closing, define, let. There's nothing to it, 10 keywords. And he said, they just could never get to the point. They were forever messing with parentheses, and they didn't get the lambda straight, and they were never even beginning to grapple with the problem. And so he was very frustrated by that, and I said, well, that's because I know this from teaching 46A and 46B, that students spend a lot of time making decisions whether they should be using a for loop or a while loop, or they can't write out simple loops fast enough. So they spend all their time on that, and the way that we've overcome that is by giving students a lot more routine practice. That by just making them write 3 programs a week instead of 1 program every 3 weeks, it really moved the needle on students getting better at the basics. And I said, well, we can do the same thing in your class. I will make you a set of exercises every week, and so that students do these very simple exercises. They're just 2 or 3 lines long, and I'll show you one here. So this is just to do a recursive sum, like the most trivial sum exercise for doing something. And so the students, he had 2 sections. One section, he didn't do anything. The other section, he said, for 2% of the grade or something like that, you do these weekly exercises. It started with 7, and then we settled on 5 for the remainder for every week. And then he had an exam in Racket where he asked the same questions that he always asks on the exams. Group number 1, where the students did nothing, did kind of terrible at the exam, as always, no surprise. Group number 2 did much better except on one question. And that was the question where they didn't get the special exercises, because I had forgotten to give them for that topic. So we wrote up this paper that says, doing these little exercises is actually very helpful. So I've given you the same 7 exercises that we've given his class for the first week of Scheme. So when they first learned Racket, they had to do these 7 things. And you're welcome to give them a try. I think they're good for getting the basic mechanics going. How do you define? How do you do cond? That kind of really straightforward stuff. How do you use let? And so it shouldn't take you too much time. And so if you want to try that, by all means, go for it. The other advice I have for the homework, other than starting early, which I always have, is to use lots of small helper functions. It's just fussy enough that if you try to just cram everything into one thing, it's just hard to debug. So I settled that every time that there was a concept, like, is something wide enough, as it was in the description, I made a helper function wide enough. I have another that's tall enough, and I have another one that says split in 2 or some such thing. So for every little thing, I made a helper function, and that made the code pretty easy to understand in the end. And then the other tip is, when you do the debugging, you have the great advantage that you can choose your random numbers in a way that's convenient for you. And I have a tip here that's, I think, so here, it says, use these 10 helper functions. And here's the testing tip. So choose the random numbers to your advantage. That way you can see, are you consuming all of the random numbers? You need to consume one in each step that needs a random number. It would be bad if you didn't, otherwise it would be very random. And that way you can also see, does it do the right thing? So I thought it was kind of, in the end, a satisfying assignment because it produces pretty pictures, and it was not really all that complex. It doesn't take a lot of lines of code, and it really is a very good practice to do the basic Lambda syntax and to get a feel for what it's like to be a Scheme programmer. So I hope that you can find the time to do it justice and that you'll enjoy the result. I'm making you read through the description of Ben Stevenson, the professor who came up with this. First of all, of course, so that you can see that I'm not the only one who gives terrible descriptions for homework, but also because he gives a bunch of interesting background that I didn't feel that I wanted to reproduce. His assignment, as you will see, is more open-ended. He invites the students to do other artistic effects. If you want to do that, by all means, go for it. But it's not required. He gave people 2 weeks, and technically I gave you 2 weeks, but there was the vacation in between. So I'm not expecting that level of engagement. The whole point is for you to have a realistic feel of what Scheme is like I said. All right. So a bit more about Scheme, Racket, Lisp. So I want to, in today's lecture, explain a little bit on why it is that I'm spending a bit of time in this course on something that really does not have any more expressive power than something like Scala does. Because there is one big difference that Scheme has, and one big advantage that it has over Scala. So, just again, brief summary. So we have this parentheses syntax. Everything is a list. A list is evaluated by taking the first element, and that's the function. And that function is applied to all the other elements that follow. So +1, 2 has the value 3. Here we have a function-like thing, define, which has the side effect of now defining here this vectorial function. So again, define takes a list, or takes the tail of this list here, consisting of 2 things. This list here that contains the function name and the parameter name, and then the body. You can have anonymous functions with a lambda. So this is the function that consumes x and produces the x times x, the square. In Scala, we have the same thing, of course. The syntax is just different. So here we have this lambda syntax. If you need local variables, you use let, or one of its friends, let star and let rect. Let takes a list of local variables and their values. So this is like the incoming environment, and then it has an expression that is being evaluated with those bindings. We have lists that are exactly like lists in Scala, except that the names are a little different. Instead of head and tail, we have first and rest. Instead of colon, we have cons. Instead of nil, we have empty. And instead of is empty, we have empty question mark. So here's how you would write a sum function. We define a function. The function is called sum. It has a single parameter called LST. If LST is empty, then the sum is 0. Otherwise, it's the sum of the first element of the list, and recursively the sum of the rest. Yeah?
I know it's an old question, so if your laptop doesn't have the lambda expression, we just use the word
You just use the word LAMBDA. Yes, absolutely. Yes, there's no penalty for it. Yeah, and that's what I expect most people to do in the homework. Yeah. In Racket, if you like, you can do a control backslash and it'll give you the line. But it makes no difference to me. All right. Now, something that is special in Scheme, in Racket, and Lisp that you don't have in other in other programming languages is that programs look suspiciously like data. The basic data structure in Lisp is a list. And a program, here, it's made up out of these lists, the same things that you use for data. And that symmetry can be put to good use. So there's a couple of functions in the standard library that take advantage of that. So I'll give you a couple of examples. So here I'm making a list of circles by taking these radius, see it, and out pops now a list that have a circle of radius 10, 20, and 30. And now I have this list of circles, and I want to put them all together into something. Well, I could call HC append. Well, but that doesn't really work because HC append doesn't want to have a list of circles. It wants the first circle, and then the second circle, and then the third circle. So there's this function called apply that helps me out. So I can say apply, and then the name of the function, in this case HC append, and then a list of the arguments, and then apply will splice in the HC append inside here, and then evaluate the whole thing. And so whatever, it's the reason that this. So over here we have something where we just take the name of this function. This was, I guess you could write something like that in Scala. The next thing, on the other hand, is something that we can't really do in Scala. So here I'm defining expr as a list of 3 items: the symbol plus, the number 3, and the number 4. That is now a list. It's a list of length 3. But so of course it also is a expression. Right? If I were to type it in at the prompt and then hit enter, then it would get evaluated to 7. So it is a mini program. The eval function will take a list that is a program and evaluate it. So it'll take plus 3, 4 as a list and evaluate it to 7.
So the single apostrophe means the thing on the right is a list.
Yes, so this means don't evaluate. I want the literal thing that's to the right. I want that list of 3 items.
There are no types here, so it's a list of like characters or like it's like a Scala any type thing.
Okay, so what now happens is it now goes through and says, what is this? This thing is what's called a symbol. And it'll then become that symbol. And this thing here is a number, and this thing is a number. So, but it is a list of any, so to speak, because you can have lists of lists. Like, let me actually show you a list of lists. Here. Right, this thing has a symbol, a list, and another list. So the lists are heterogeneous. And that, I guess, is a difference from Scala, where lists have a type. And here we rely on the fact that you can put, like, arbitrary stuff inside a list. Yes?
Is eval already inside the libraries? Or
Yes. So eval exists. It's and we'll see. It's a scheme function. Okay. Yes.
I try it on the code and say the plus is unval identified.
You tried what?
The second one.
This one?
Yes.
Oh, let's try it.
you want to try this code? How should
should we define circle?
Oh,
Or input slideshow.
yeah, well, for this one, you have to change to that other dialect. If you want circle, I can't remember what the dialect was called. Okay, so here's expert. So here I say expert is the list containing plus 3 and 4. You can see what expert is. It's the list containing plus 3 and 4. And then when I eval it, then it's 7. All right. Now what's the point? I'm going to be using apply and eval to give you somewhat non-standard ways of implementing factorial. So I'm having here a function range that, let me just show you what it does. So when I say range from 1 to 100, as you can see, it makes me a list of everything from 1 to 100. So, and you can study the definition. It's a straightforward recursive call. So now I'm defining factorial, saying the factorial of n, make the list of numbers from 1 to n, which is this list that you've just seen, and then apply asterisk to it. And that'll do it, right? Then I multiply them all together. Here I give you an even more interesting way of doing it. I say, make that list from 1 to n, and stick a asterisk in front of it with cons. That gives you a list of n plus 1 elements, the asterisk, 1, 2, 3, and so on. And then pass it to eval. That'll also multiply them all. Now, what's special about doing it this way? So here what I'm using is that that I can build up data by using the normal constructs. Here I'm building a list of numbers, and here I use cons, and so I'm building a list of more things, and so that's data. And eval can take data that represents code and compute what it is. So data is code, and that is the genius of Scheme or of Lisp. When it first came out, that there's no difference between code and data. That a program is a list, and Lisp is a language to consume and produce lists. Yeah.
When you do that sort of thing, doesn't it make it harder for the compiler to optimize?
Oh, sure. I mean, I'm not saying this is efficient or anything, but and in fact, when you do similar things in JavaScript, right, where you could use eval, eval is always a really bad thing in JavaScript because, for one thing, it's insecure, and who knows what that code might be doing, and it's hard to reason about it. In JavaScript, also, when the eval function is not nice, because what does it take? It takes a string. So JavaScript has to parse out that whole string. You might have syntax errors in the string, for example, and and also it means that it has to be a whole little parser inside JavaScript. In Scheme, lists are an elementary building block of what the thing does. So if you now have a list of tokens, there's no parsing that needs to be done at all. And so that's the interesting thing, that you can make programs that produce other programs. You can make programs that consume other programs just in the exact same system. So there is a famous book that if you have some extra time over the summer, that it really is a good read. It's this book called Structure and Interpretation of Computer Programs by Abelson and Sussman. You can download it for free these days. And so it talks about Scheme and how Scheme is implemented. So it talks about all of these things. How do you implement functions, for example? It does basically for Scheme what we have done for SL1. Now, it shows how to do function calls and all of that good stuff. This yin-yang symbol that you see here with eval and apply, so it's their thing that they say that eval and apply are used to define each other. So So eval is a function, and it's the fundamental function in scheme. That's what happens at the read eval print loop. It reads the list that you type, it passes it on to eval, and it prints the result. So eval being written in scheme, it's scheme. So here is the source code of eval from Abelson and Sussman. So eval takes an expression and the binding of the three variables in that expression, and it now goes through a bunch of things and says, is it a variable, is it coded, is it an assignment, is it a definition, is it an if, is it a lambda, and here's the most interesting case where it says, is it a function call? If it's a function call, then the function is evaluated, and then apply is used to apply it to the list of arguments. And apply is a scheme function that at some point calls eval. So by evaluating the body of the function in the bindings of the parameters. So I don't want to get into any of these details. They're a little bit tedious. But the point is that you can implement eval in scheme, so that eval will take any list that is a scheme program and evaluate it. And when you do that, then you can do something that's actually kind of amazing and mind-bending. Of course, you can then use your eval to feed it in like a let that contains a definition, let's say let rec, that contains the definition of a factorial, and then you compute 10 factorial or something. And then eval will crunch through, and just like our SL1 interpreter, and ultimately print you the value of 10 factorial. But you can do one more thing that I don't know how to do in SL1. You can make eval read the definition of eval, which is after all a piece of scheme code, and then have that read the definition of factorial and compute 10 factorial. And then eval will go through the definition of eval, which consumes the definition of factorial and evaluates 10 factorial. And it actually works. So it's always an amazing thing to do. And if we had more time, I would give you an exercise with a slimmed down version of scheme where you would do exactly that. And of course it takes a long time and it's kind of pointless, but it is amazing that you can have a program consume itself. Yes?
Is that sort of like the Y Combinator?
It is kind of similar to the Y Combinator. And so yes, if we have some extra time, I'll go down the Y Combinator. So but it is kind of similar. In a couple of slides you'll see that too. Yeah. So it is kind of stunning that you can do that. Now SL1 is not powerful enough to do it, right? Well, maybe SL1 together with lists. We could, with a great deal of trouble, like re-implement that Scala code in several hundred lines of SL1. Scala is very compact. So it's worth a try. But we're not doing it. So why do we care? The reason I care, or why people care, is that it gives a much more intuitive way of understanding certain limits of computation. So when you're going to take 152, which is a required course in the program, they're going to teach you, amongst many other things, what a Turing machine is. Turing invented those Turing machines before computers ever existed to understand what things can be computed and what things can't be computed. So Turing's insight was that there were certain things that are easy enough to explain, but they're uncomputable. And he came from it from a mathematical point of view, that the equivalent mathematical formulation is that there are theorems, mathematical theorems, that are true, but you can't find a proof for them. Which is kind of strange, right? You would think that everything that we've ever learned in math, there's a theorem, and then you supply the proof, and that's how you know the theorem is true. So there are theorems that are true, but we can't come up with a proof for it. Similarly, there are programs that we cannot write. And so the one that he came up with is this halting problem. So it's kind of amazing that he had an intuitive understanding of programs that can consume programs before there ever were computers and programs, but that's why he was a very smart guy. So we now understand this. We can have a scheme program that can consume another scheme program. And so that means that there's certain things that we might want to do. Let's say that I'm teaching a semester-long course in Scheme. I'm getting homework assignments from hundreds of students. And one of the things that I would really like to be able to do is I would like to write a program, might as well write it in Scheme, that consumes your solution and my solution, and it says they are identical on all inputs, or they are not identical on all inputs, right? If I could write a program like that, I could fire the grader. Right? And it would be much better than the grader, because the grader only tests it on a bunch of sample inputs. I would have the answer for all inputs. Now, before you go on and raise venture capital on this great project, you have to know that it's impossible to write such a program. So this is one of the programs that seemed like easy enough to explain, right? Read a bunch of Scheme code, read another bunch of Scheme code, and you would think there would be some algorithm that looks at the code and says, okay, what does it do? There's a recursion in here, there's some function definitions, and how hard can it be to say this is what this program does compared to that, and write, these days you could maybe machine learning, right? So there ought to be this checker that can check whether two programs do the same thing. So that's not the checker that Turing looked at. He looked at a checker that checked at a slightly simpler property of programs. So he said, this is also desirable for grading. Every once in a while, I grade one of your programs, or the grader does, and it doesn't seem to come to an end. It just sits there. And the grader wonders, or I wonder, is it ever going to end? Or is it in an infinite loop? And you wait another minute. And it still doesn't end. You say, okay, will it ever end, right? And so this is a thing that ought to be answerable, right? You have a Scheme program, and in Scheme you would have infinite recursions. And you should be able to analyze the structure of that program and say, does it have an infinite loop sitting in there? Is there some input that makes this program go into an infinite loop? Or, on the contrary, will it come back with some answer? Maybe not the right answer, but an answer after a finite amount of time for all inputs. And so that's the halting problem that Turing said is unsolvable. That no one can write a program that can look at an arbitrary program. A program here is a Scheme program, a bunch of defines and lambdas, just a list of those things. No one can write a program that looks at that list of defines and lambdas and variables and lets and say, this thing will terminate on all inputs, or this thing will have an infinite loop on at least one input. Which doesn't seem intuitive that should be so. But the proof that this is unwritable is amazingly simple. So what Turing said, except Turing put it in the context of these Turing machines, which are much fussier than doing it in Scheme. So I'll translate it to you. So Turing's argument is, let's say that we could write a halt checker. What would a halt checker do? It would take a lambda, and this is data, so this is a quoted thing. It would take a lambda with some expression in here, and then would analyze that expression. And it would either return true if the expression here terminates for all possible inputs x, or it would return a false if there is at least one x for which it fails. So now let's just assume that after a few $1 million of venture capital, we have written a halt checker, which is probably somewhat complex. But ultimately, it is a Scheme function. It is something that takes an input, and then on that input, whatever that input may be, produces either true or false. All right. Now, given this possibly long and complex piece of code, I'm now going to define another function that I'll call k. K is the function that has an input x, and now it runs the following code. It says if halt checker of x is true, then it goes into an infinite loop. Let me show you why this is an infinite loop. I have a let rec here. I'm defining a thing called loop. Loop is defined as a lambda with no arguments that calls itself. So, and then I execute loop. what will that do? It'll execute this thing loop, which calls itself, which calls itself. So I'm saying if halt checker returns true, my function k will go into an infinite loop. Otherwise, my function k will say true. That's what my function k will do. Okay, what's with that? And so here's, someone said, where's the lambda? So where's the y combinator coming in? This is not quite the y combinator, but it's kind of a similar idea. I'm now asking, what happens when you apply k to itself? K is, as you can see here, a fairly simple program. Okay, it's going to be a complex program if I put in, I have to put in another let and put in the definition of halt checker. Then it's going to be a little longer, but it's going to be a finite mess of lists and lambdas and whatever. So, what is k when it consumes itself? Well, let's see. K is this thing. So, in this case, x is k. So we're checking whether the halt checker, what does the halt checker think of k? And let's say the halt checker thinks that k always terminates. Then it sends it into an infinite loop. That can't be, because that would have meant that the halt checker was faulty. If k has an input, namely itself, that sends it to an infinite loop, then the halt checker must say, this thing returns false. That's the job of the halt checker, to return false when the thing can be in an infinite loop. So that can't be. So obviously, this branch here was not taken, and k of k is true. But in that case, the halt checker must have not found out that k always terminates. And so the halt checker must have lied. Either way, the halt checker can't be as good as it should have been, because it's been fooled by this construct. And so that's an impossible to resolve contradiction, and what it shows is that you cannot write such a halt checker. Yes?
But what if it was just a few special inputs like that? Like, what if you could write a halt checker for maybe 90% of programs?
Well, that's not what Turing estimate said. Yes, that would still be useful, and you could raise venture money for it, but the Turing estimate is the one that works for all inputs.
Because most programs you look at, you can analyze it.
No, sure. That is a huge difference between theory and practice, right? In practice, you could quite possibly write a very useful program that analyzes real-life programs, but you can't write a universal.
Yeah.
And so but it is a kind of an amazing theoretical fact that certain computations that don't look like that hard are impossible. And out of this one, you can derive any number of other programs that are impossible to write. Like my equality checker that takes two arbitrary programs and always tells you whether they're the same. Can't be done. You could always fool it with some inputs. So anyway, so this is not a result that has any practical use necessarily, but it's from a theoretical point of view, it's fascinating to know that some things just cannot be done. They're just impossible. The world is a strange place that even though you can ask very reasonable questions, you can't always come up with answers, and you can prove this. Now, like I said, Turing proved this in a cumbersome way with Turing machines, and then you had to argue why a Turing machine can simulate another Turing machine. And it's a long and involved proof to do that, and it's not super interesting, and it takes pages and pages in his paper or in a textbook. And if you take 154, you may well have to suffer through that proof. And it's not super illuminating. But with Scheme, where it's so clear that a program can consume itself, I think the proof becomes much simpler. And so that's what I wanted to show you, that having code equal data is a powerful concept, and it can even lead to these interesting results in a way that I can put on a single slide and not have to come up with a whole new machine concept and stuff. All right, so that was the one thing that I wanted to show. The other thing, why code equal data is useful, is that it can expand what you can do in a programming language. So you know that when you write a program in Scala or in Scheme, what can you do? You can define new functions. And that's pretty much your extensibility point. Okay, in Scala you can write new classes. But wouldn't it be nice if you had some other way of producing new programming constructs? And I'll give you an example of one that I'd like to have. In Scheme, where we have side effects, here I give you a few functions with side effects, like printing or setting a variable. When you have side effects, it becomes now attractive to have a loop. Now you haven't seen how to write a loop in Scheme yet, but let's say I could invent a programming feature that has this syntax here. So I would like to be able to introduce a loop where you say while x is greater than 0, I put a little keyword do here just for beauty, and then I put a bunch of statements. And it's clear what this function should do, right? It should check if x is greater than 0, if so, it should execute the statements here, then it should come back here and check is x still greater than 0, and so on, just like a normal while loop in every other language. Now I want to write this thing. Scheme doesn't have it. Can I do it? Well, kind of. In Scheme I can write a function. So let me try that. Now I don't get this syntax here with a while here and the do there, but maybe that's fluff, so I'll just call my function while-do. But now I run into a problem. I can't put this expression, x greater than 0, I can't put it just like that, because if I do that in Scheme, then the expression will be evaluated and its result will be passed to the function, and then it'll never be re-evaluated. So if x happens to be 10, then greater x 0 is true, and my while function would only see true. I wouldn't see a piece of code that sometimes is true and sometimes is false, because that's how evaluation works. If you have an expression, it gets evaluated. Now, of course, there's a simple trick to avoid that, and that is to put a lambda around it. Anytime that you want to defer evaluation, you can say, I'll put it inside a lambda with no arguments, and then it's the responsibility of the while do function to invoke this thing, and then I dynamically get the value of greater x equal. And I do the same thing with the body here. I put it inside a lambda. And that will, of course, work, but it's not so pretty anymore, right? I mean, if you read this here, I mean, it's kind of icky to see all these lambdas. So this is where macros come in. With a macro, you can say, I don't want while to be a function. I want while to be something that happens before the program runs, that rewrites the program text. So that when the interpreter sees while, that somewhere else it sees a definition for what while should be, and then it rips out this list here of 1, 2, 3, 4, 5, 6 elements, and replaces it with some other list that is some equivalent code, and then it starts evaluating. So that's what a macro does. A macro is not evaluated when the program runs, it's evaluated when the program is translated. So I'll give you a simple example on how you can define a macro, and I'll start it with a simpler one. I'll start it with a swap macro. So here's what I want to be able to achieve. When I call swap u and v, then I want u and v's contents to be swapped. Now notice, this is not something that I could ever write as a function in Scheme. Because in Scheme, like Java, for example, or like Scala, has call by value. That means if swap was a function, it would receive the contents of u and the contents of v, and the swap function would have no way of modifying what u is and what v is. It just gets a copy of the contents. But I want it so that after I call swap u and v, that u is what v used to be and v is what u used to be. For that, you truly need a macro to do that. So what I want to achieve is that this thing gets ripped out of the source, and some set of instructions that said, set u to something, set v to something is instead sufficed it. So the define syntax construct that you see up here does exactly that. So define syntax says, whenever you see a swap with an exclamation mark, then you should do something special. the way that defined syntax works is a little bit arcane, and we're not going to look into the details. We'll just learn it by example. So defined syntax needs a thing afterwards called syntax rules. There's other ways of doing it, but that's the one that I'm going to do right now. So syntax rules has a few parts. The first part is a list of keywords. There's no other keyword that I want, so I'll leave it blank for right now. You'll see in the next slide where the keywords come in. Then I have another list. I don't know why it has why these are like that, but it's the way it is. And this list here has two parts. The first part is the pattern that I want to match. So the pattern says, whenever you see something that starts with swap exclamation mark and followed by two other items, then I want you to rip it out and replace it with this thing. So what is this thing? It is the set of instructions that you need to do the swapping. It's a let. I define a local variable C that I set to A, and then I set A to B and B to C in the normal way that you always swap things, like a circular three-way thing. So when the swap UV is seen, then it gets replaced by a let, by this very let here, of course with A and B being replaced by U and V. So that's what a macro does. It takes the program text and it rewrites it into some other program text following some rules. Now, the way Scheme does it is what's called hygienic. That is, it knows about some common pitfalls. So, for example, what if I call swap XC? So the naive way would be to say, okay, so that means that every A becomes an X and every B becomes a C. But that's not actually what you want, because I have another C here, right? And then if this B becomes a C, then it wouldn't work. And the Scheme macro mechanism knows about this possibility, and it will rewrite conflicting variable names. So when it sees the C, then it'll say, oh, there's another C in here, I better be careful and call this one C_17 or whatever. So that's a simple macro. We have to work a little bit harder to do our while macro, and here it is. So it's again defined syntax. That's then we have the name of the macro, while. Then we have the syntax rules thing that says our macro will use syntax rules, this pattern matching. We're informing the macro that if it sees do, that do is another keyword. And you remember the way that I want to use the macro is like this: while, something, do, and then more stuff. Now, the next thing I call condition. That's that list that I want to evaluate for each time. And then after the do, I can have more than one statement. And the way to do var args in the syntax is to do, you give it a name to all of them together, and the ... means that there can be any number of them. So now I'm going to have to rewrite it in some way, and I have to write it into a loop. That's kind of similar to the loop that you see in the halting problem. I'm defining a function called loop, and then later I call it. And what the loop does is it checks whether the condition is true, and if so, then it wants to run all of the statements in the body, followed by another call to loop. So that will eventually call the loop again and again until the condition is false, and at that point I return false. I have to return something, everything has a value. And then we'll start unrolling the steps. That's the rewriting that will work for me. Notice over here, I want to execute all of the statements in the body, followed by one more call to loop. So that's multiple statements, and I can't cram them all inside the positive part of an if. The positive part of an if takes a single statement, so I'm using a trivial let to group them all together. So that's just a syntactical license. If for whatever reason you need to do multiple things, and which only is something that you do when you have side effects. But yeah, if you want to do multiple things, you can do a dummy let, and then that'll work. So that's my rewriting of the of the while loop. Every time that a while is seen, this somewhat more complex thing is going to be spliced in, and then they'll loop it. So this gives you a marvelous way of taking a language and building other features on top of it. So in fact, things like let star in Scheme are macros. They're defined in terms of other primitives. So there's a way of doing recursive definitions, and I'm not going to get into this because we're not really going to be writing macros. I just want you to know that this concept exists. And the details get complex quickly, so if you want to click on these links, you'll see where people are struggling with how to do this in real life. And you could imagine that things do get kind of complicated because you want to write things that are natural for programmers and edge cases and whatever. But still, it is a relatively simple way of being able to extend a language in a way that you could not do in a convenient way by just providing other functions or other classes. And so it's a desirable thing. So other programming languages want to do this too. So in the C language, you can kind of do something similar in a half-assed way, which describes C pretty well. So the designers of the C language said, sometimes we want to do this thing where we want to have a change of the program text before the program gets compiled. And you use these preprocessor definitions for that. So in C, you can say pop define, and I'm doing the swap thing here again, swap of x and y. And then every time that swap of x and y is encountered in the program text before it's fed to the compiler, then this textual substitution is made. So how could I define swap of x and y in C? Well, maybe this is C++ because I don't know how to do this in C. The difficulty is I need to declare a new variable, and it has to have the same type as x. In C++, I can say auto, and then it'll automatically have the right type. I don't know if in modern C this is also a thing. So I'm saying if temp is x is y, y is temp. That's easy enough. And then whenever swap of something, comma something, is encountered in the program text, it's ripped out, and this whole thing is put in where, of course, x becomes the first argument of swap, and y becomes the second. Does it work?
No.
On a happy day it works, right? If what you're trying to swap is simple enough, swap of A, B will work if A and B are simple variables. But if you try something more complicated, then it does this dumb textual substitution, and that sometimes doesn't work. So if I say swap of AI++ and B, will it really swap A of I and B, and then increment I? And the answer is no. Because it'll stupidly put AI++ here and here. It'll make temp the contents of AI, and then AI+1 will become Y because the thing has been incremented. It's just textual substitution. What if you happen to have two variables called temp and temp2, and you want to swap them? Will it do the right thing? No, of course it won't. Because it'll just say auto temp equals temp, and that won't even compile. So these macros are not very smart, and that's where Scheme goes through a great deal of heavy lifting to make that possible. I don't think it would be possible in the context of C to do all of that, because you can really splice an arbitrary text, and really it's just a text editing mechanism. So other languages that were inspired by the success of things like Scheme said, this is such a powerful feature, we want it. We want to be able to have new constructs in the language. And so both Scala and Groovy, amongst other languages, have this capability where you can define a macro, and then they kind of go the Scheme route and say, what's a macro do? It takes a piece of program text and it transforms it. But what is program text? To do it literally, we know from C that's hopeless. You really have to parse the thing out to understand it. And so in Scala, if you want to write a macro, you have to basically write a compiler extension that consumes a piece of parse tree and then transforms that to another valid piece of parse tree. That means that the macro writer in Scala has to have an intimate understanding of what the structure of that parse tree is. And so people do that in Scala. There are macros out there. For example, assert that you've been using in Scala test is a macro. And the maintainer of assert in Scala test has to understand what could be passed and how could he or she transform that. And unfortunately, it seems to be a little different in every version of Scala, so there's a certain pain point in keeping track of that. Because the internals of a parse tree are things that are not particularly canonical. It's not clear what should that parse tree be and how constant it is. Whereas in Scheme, you know exactly what the parse tree is. Opening parenthesis, keyword, more lists, closing parenthesis. That's your parse tree. And so it's trivial in Scheme to do this kind of rewriting because you don't have to worry about the structure. To do this in other languages is much, much harder. So that's the power of a language that has a very simple syntax that becomes very easy to operate on itself. Yes?
Rust has a pretty nice macro syntax and
Okay.
types and everything.
Okay, yeah. So I mean, macros are something that you want to have. And so the simpler your language is, the easier it is to have a macro system. All right, so the real thing about kind of the killer feature of Scheme is that code is data. So I thought I'd give you a little lab where you try out something. There's two parts of it. Ignore step 2. We're not going to get to it. And so in step 1, I just want you to write another macro. So just get out racket and put in, you leave the pound-lang racket in place, and you can just try this out, how this works with while here. So when you execute this thing, and now we do something with while, where do we have a call? Put it in the pane here. Oops. Yeah, I'll put it up here. Oh, now it says X is an unbound identifier, so I guess I need to define it. Can't blame it. And now it does what you think it does. It prints the countdown here that the while loop indicates. So we want to do the same thing with this for loop. Here's my for loop. So I want to be able to say for I in, and then some list. Here I happen to have a quoted list, but it could be any list. Do, and then I wanted to have it do some kind of actions. So I want you to write a macro that does a for here. So the first thing you need to ask yourself is, when you see this code here and you are the macro processor thinger inside Racket, you're going to rip it out and you're going to replace it with some other code, with some other list. What is that other code? So ask yourself that question first before you do anything else, because if you don't know what that is, you won't be able to progress in this. All right, so take a few minutes, think about that. Then we'll talk about what code that is, and then we'll see how to get from there.
Let is just like, it takes a very basic and expression.
Do you want to do expression final this time around? I guess I can do it now.
Yeah, well, it's kind of
You're trying to get that
can't even keep track anymore. Got so many lines. Anyways, okay, yeah, sure. Then I'll just like look for your name for earlier.
I think that's exclamation mark. I think we have to use that as communication. It's just so it's mutable. Or
I'll find your name.
Yeah,
Okay, so,
Exclamation mark. But I was wrong. So communicating with value.
So, for while, it's up as if condition, and ultimately, that condition will be true. Or if that condition will be true, it's false. And then,
It's with side effects.
it only calls it calls itself.
Anything that changes procedures.
This solution, we call that exception. But in conditions,
So that's exactly it.
the condition will halt, but the halt condition is so it'd be something like if. So condition is true if like I is the length.
I just can't use the
for my inside.
Okay, I see. Yeah, it's like using it or
But that one has found condition.
Not true.
the extra copy.
This gives me to that's pretty this.
So I think we need a person where, like, I just heard it a while. Maybe if we put
Okay, before people go too quickly into the wrong direction, because I heard a bunch of people saying, "Oh, I'm just going to write this for loop into a while loop." Let's figure out why the hint says map. So what are we trying to do here? So we want I to assume 1, 2, 3, 4, 5, and for each such setting of I, we want to compute what this thing is. Now that's exactly what map does, right? For each of the elements in a list, it calls a function, and then it executes the body of the function. So if we can rig it so that the function does this thing, then we can use map. So what we would do is we would call map, and map takes 2 arguments. I can never remember, does the function come first or does the list come first? All right, so half of us. Okay. I think the function comes first in Scheme. So let's try it. If not, we'll just reverse it. Okay. So we have a function, and then we have a list 1, 2, 3, 4, 5. Okay. Now, how do you write a function? Lambda. Then it has an argument, and then it has a body. Well, I know what the body is. That's the body, right? And what's the argument? I, and that is what is the genius of this thing. Notice, I don't have to do any mutation here at all. I didn't have to set I to one thing and then set it to another thing and set it to another thing. That happens automatically, because when this function gets called, first of all, it's going to be called with 1, so I becomes 1. That's how functions work. And then the 2 comes in, and then I becomes 2, and so that same I is then used later here. So I'm getting the correct value. Okay? So that's the transformation you want to achieve. Let's double check that we got the function the right way. And yes, so this one here, then prints 1, 2, 3, 4, 5. So it does this thing. And that's the code that you want.
Is new line what is new line?
New line is a function that prints a new line. Let's try it out.
The syntax here is
Yeah, it's not the most elegant thing. There didn't seem to be like a print on.
well, it is a little function.
All right, so that's the rewrite that you want to achieve. So go ahead and write your syntax rules thing so that there's not a while here, but a for with the various bits and pieces. And then here, then there shouldn't be a letrec, but instead there should be a map with its various bits and pieces.
Over here is like the signature reading, right? The long function. So we can just change that to so what we're going to need is
should we just do this? Should we have do the middle and then it's a number and we're going to put the body like
4 elements to the body.
Let me do that. Because like I don't know if it's a body, so
we need that. We need to just name the elements. We already have concept. We only need that variable.
Oh wait, I didn't put up. Oh yeah, I see.
We don't need new line because we just do that. We don't need pen. And then we need a separate. So we need an I. And we need the list. And we need the function. So,
Batch or batch.
so you can give us a number, right?
okay, so it would be 4 variable. So instead of 1 condition is line, it would be 4 variable. So, see that line? Elaboration. While condition be line, it would just be 4 variable. Wait, so it would be 4 variable in list. What's a variable? It's just the name for the round.
Oh, that means false. We don't need that.
Do body that so that's
One argument, right? It's like the
so here's the hard part. I don't know this syntax.
Yes.
Well, the way I interpreted it is that each so for this one it's 1 condition defined, right? And then over here it's while this is the condition, do the rest. So while this token assumes while this condition assumes this token do assumes do body assumes everything else.
Bad sequence trying to make fun.
And that is what we do with these tokens. These tokens get represents the addresses and stuff. So while represents while condition represents this to the body represents. I don't know if this goes to how he plays around with while switching to the body. He doesn't use it a lot because you just use it as a way to recognize that's what you get. So remember in Robert Sicilides here, we use factors and
Professor, what does this say? Body is a sequence of
and then turn it into a function.
Terms.
That's what we're doing here.
Oh wait, it's right here. Right.
So it's that reading this whole thing as if it's a string.
All right, so let me just do this here real quick. So we have to rip out the first part and put in the for stuff, and we have to rip out the second part and put in some map stuff. Oh, and with the syntax rules, we have to put all the keywords. I think we have 2 keywords, right? We have in and do. That just tells it that those things need to be treated verbatim. And so now I need to make a pattern. So I say for, well, I can't say I, right, because it might not always be I, so I call it var for a variable, in, and I call this thing values, do, and then I have the body as a var args. That's my pattern. Okay? And then I need to rewrite it as a map. So I have the map down here. So it's a map of lambda of something. So what's the something? Well, here it says I. Well, what do I now use?
Var.
Var, right? Because I want whatever variable was provided, I want that to go in here. And inside here, I want the body. That's how you do it. And the argument of the map is, so I have map, a function, and
You need a range.
what's it going to be?
Values.
Values, because that is the thing that I want. Okay? And that should be all. I guess I must be short of parentheses. So let's try it out. Oh,
I got the same thing.
what did I do wrong? Here I have to put in a 4. I know. Okay, so here's another nifty thing that you can do. When you click on macro stepper, then it shows you here what the input was. There's 4 I in do whatever, and it shows you here how it rewrote it as map lambda I print I. What's that?
Can you show that again?
Yeah, I clicked on this button that says macro stepper. And that's all I know about it. When you click on it, it shows you the before and after. And so again, the point is that this thing is just a list, right? It's just a bunch of program text as a list. And it got mechanically rewritten as this other list. That's what a macro does. Okay, so that's stuff that's all fairly easy to do in Scheme because Scheme has this very nifty and regular syntax. That's all we're going to be doing with Scheme in this class. So I wanted you to have seen what it's like. You have one homework where you can kind of get a bit of a feel of what it's like to program with a bunch of parentheses. But the power of Scheme comes from code as data and data as code. We'll be moving on Wednesday with looking at types. We'll have a couple of lectures on types, and then I've changed the order a little bit, and we'll then move on to Prolog before we go to the final thing and actually write a small compiler. All right, get started early with the homework, please. It's not a difficult homework, but it is fiddly and tedious, and you don't want to face it half hour before it's due.